Okay, we've reached the programming stage of episode 3. Again, if you're doing the Python track, you can skip right on ahead to segment 5B. Otherwise, stay here with me and we'll do the R stuff. You know, this episode has not been very computational. It has been much more theoretical. We've been talking about these abstract notions of linear independence and the span and the basis and stuff like that, none of which lends itself particularly well to computation, but there are a couple things we're going to do. In particular, I want to talk about two things, how to do them in R, especially because we're going to be using them later, which are functions and loops. And these are two components in every programmer's toolbox and are available in every programming language. Now, if you've done programming before, this may seem like old hat to you. If you haven't, let me just say that I'm concealing a lot of complexity here. I'm basically just giving you the very basics that you need to do to be able to do some exploratory playing around with linear algebra concepts. If you want to understand really how functions and loops work and get some better practice with them and building complex programs with them, you really need to take a programming course, which I'd encourage you to do if you're interested in that. So let's look at the cheat sheet here, and we're going to be looking at functions and loops, in particular the for loop that R gives us. And these are two, like I said, rather heady concepts that I'm going to sort of go over and give some basic examples of. And then we're going to talk about how to do some plotting, because that's going to illustrate some of the linear independence principles in this thing. So first, functions. Let me explain that a function is essentially like a building block of code, some coherent chunk of code that a programmer wants to be able to execute multiple times in multiple different places. So the programs we've been doing so far have been, to start at the top and go straight to the bottom line by line, and they haven't had any organization to them. They haven't had any subcomponents or been broken up into parts, any nonlinearity. Functions give us that. And if you've taken all the math volume 1, you may remember functions from there, right? It's a mathematical notion where you have an input and an output. You have a domain and a codomain, and for every input, the function gives you a value for the output. It's essentially what functions are as well in programming languages, and that's how they got their name. What we're going to do is say there's an input or perhaps more than one, and when we call the function, we are giving it certain inputs and getting back the output that goes along with that. And here's the syntax for doing that in R. We're going to say the name of our function, and you should name it something meaningful that actually tells you what the function is doing. And then we're going to use our little arrow, which is the assignment operator, and then the word function, literally. And then inside bananas here, we're going to have a comma-separated list of the inputs to the function, which are always also called arguments, as I mentioned before. It's kind of a nutty name, but that's what it's called. By the way, it is possible to have a function that takes no arguments, and then you just have an empty pair of bananas here, and that actually comes up more than you might think. Then we're going to have a curly brace here, which matches a curly brace down here. And you got to get in the habit of realizing that every time you have an open curly brace, there's a corresponding closing curly brace somewhere, or there should be, just like Noah's Ark, where the animals go on 2 by 2 here. And then inside here we have the statements of the function. Now what this means is that all of the statements here, which is just any kind of R code that we want to do, any of the stuff from last time or things we'll learn in the future, you just list inside the curly braces, and that means that every time the function is invoked, every time the function is called, all of those statements are going to get executed. And then whenever R encounters a line that says return like this, that is its way of giving the output back to the code that called the function. Okay, so this is your inputs in here, the arguments, and then the output is what you get from the return statement. And one thing I've noticed through many years of teaching introductory programming is that functions are the hardest thing for beginners. And really, it's not because the concept is hard. It's because it's difficult to understand how the wiring goes back and forth between the code that calls the function and the code that is the function. And especially weird is the fact that the variable names, the names of the arguments, may not be the same in the function as they are out. And in fact, they're normally not. Okay, so most of this is best learned by an example, so let's do one. I'm going to write a function here called linear combo. And this is going to be a function that computes the linear combination of a set of vectors. And we're going to use function here. And inside, I'm going to give it 2 arguments. I'm going to call them n1 and n2. And that's going to be how many of the first domino you want, and then how many of the second domino you want, right? So the number of domino 1 and the number of domino 2. And what it's going to do is return a vector, which is the linear combination of them. Now inside the function, I'm going to say, let's make a variable called domino 1, and we'll set that equal to the vector 1, 2, that's been our running example in the yellow domino case, and then we'll make a domino 2, which will be 4, 4. And then, really, I'm done. I just have to return the answer. What is the linear combination of n1 of the first domino and n2 of the second domino? We know that it's n1 times domino 1 plus n2 times domino 2. So by saying return here, that means, hey, whoever called me, this is their answer back. Okay? So I'm going to source this. And now I'm going to go down here and I'm going to say, what do we get when you take a linear combo and I'd like 3 of the first vector and 4 of the second, please. It gives me back the vector 19, 22, and you should verify that that's the correct answer for that. If I say I'd like 3 of the first and 0 of the second, it gives me 3, 6. And if I say I'd like 0 of the first and I'd like 100 of the second, it gives me 400, 400, right? So every time I'm calling the function, that's what it means when I write down the name of it and then have bananas with some arguments inside, that's calling the function, making it run, I get back the answer there. And if I want to save the answer in a variable, all I have to do is say something like Bob, or whatever the name of the variable I want is, arrow linear combo of 5 and 5. And then if I say Bob, I now have a variable Bob, which is the vector 25, 30, right? So it looks a little weird. You're basically saying assign Bob the function, but what this means is that I'm calling the function, I'm giving it the return value back. Now again, the thing that messes up students when they first learn programming is this. I could also make a variable called n1, set it equal to 3, n2, set it equal to 4, and say linear combo of n1 and n2. And that gives me the same answer as I had up here, right? So now I've named the parameters here. Now, that may not seem weird at all at first, but here's the part that gets students messed up. I could say Sally gets 5 and Dave gets 2, and then say linear combo Sally, Dave. And that's 13, 18, right? Which is the same thing I would get if I had said I want literally 5 of the first and 2 of the second. This messes people up, I've noticed, because, Sally is a name given down here to the first parameter, the first argument, but up here in the function, we're calling it this other thing. And what you got to realize is that the names of the arguments in the function are basically what the function is going to call whatever it's given. The function basically says, hey, you're going to give me 2 things if you want a linear combo of these dominoes. Give me how many you want of number 1. Give me how many you want of number 2. I don't care what you call those variables. I'm going to call them n1 and n2. You can call them n1 and n2. You can call them something else. You don't even have to call them anything if you don't want. You can just say linear combo banana 5, 3 banana and be done with it. But I'm going to call those things n1 and n2 inside the function. Those names are none of your business. All right? So let's look at plotting. In plotting, it's a little bit of a pain in the base R package, but just get over this because then we actually have it easy on the Python people with this part. It's easier than it is in Python. What we're going to do is set up a plot by doing this nutty line here. Now let me explain what this is. We're going to call the plot function. We're going to give it 0 and 0. That's because we're really just setting up the plot. We're not actually plotting anything with this line. And when we say type equals n, that basically means no plot, please, which I know sounds weird because we're calling the plot function. So why would you call the plot function and not want a plot? Well, we do eventually want a plot, but this means not right now. I'm going to add my points separately. That turns out to be the easiest thing to do for a lot of things. So I'm going to say plot nothing at all and set the x and y axis limits to be these things. So I'm giving a vector here to xlim and ylim, and the vector is the minimum x value and the maximum x value, the minimum y value and the maximum y value. Actually, those shouldn't be minus signs here. You often give it negative numbers there for the first one, but I shouldn't have said negative min x. I mean, you're actually giving it the min. Okay, so let me show you how that works. So I'm going to come down here and say, well, actually, let's just do it in our program here. Let's come up here and say plot 0, 0 type equals n. And what I want to do is say my x limit is going to be go from -5 to 5, say, and my y limit is going to be from -5 to 5 also. So that tells me where I want my axes. Okay. Now, let's make a random linear combination. So remember how we do a random number in R. We can say R unif, and we tell it how many we want. So we'll say we want 1. That gives us a number between 0 and 1, and maybe I want a little bit more range than that. So I'm going to take that number, which is between 0 and 1. I'm going to multiply it by 4, so that now it goes between 0 and 4. And I'm going to subtract 2 to center it. So now it goes from -2 to 2. And I'm going to assign that to random n1. Similarly, I'm going to say, let's get another random number and set that to same thing. So when I run this thing, what did I do wrong here? Unexpected banana, because I have too many bananas there. All right, so I run that thing, and notice it set up an empty plot for us. That's what this line of code did. And then if I go down here to random n1 and random n2, you'll see that those are both random numbers between -2 and 2. And if I run this thing again, we'll get different numbers for those. No, we won't, because it restarts the seed. Yes, we will. Sorry, 0.07. So every time we run this code, we're going to get different numbers for our random n1 and random n2, right? Okay, so now let's make our random LC. So that's the random linear combination. We'll call our linear combo function, that's nice and handy, and we'll give it random n1 and random n2. And let's run this thing. And now if we say, hey, what is my random linear combination, I'm going to get that. Now we know this could be any point in the plane, right? Because we know we can get any point with these two vectors. Let's plot it and see where it goes. So we're going to say plot. We're going to say plot the first component of random LC versus the second, because the first one is its x-axis coordinate and the second is its y-axis coordinate. And the way we do points here is we say points and we give it the x value and the y value to add a point to the graph. And by the way, I shouldn't have said plot, I should have said points. Then another thing you can do is you can say comma call equals, if you want to set it a color, I'll make it blue. You can also say PCH equals 19. I like doing that. That basically gives it a certain plot character that's kind of a nice little circle to look at. So let me run this thing here. And now you'll see that we have a point popping up on the plot here, right? And that is the point whose linear combination we just generated randomly from our two yellow dominoes. And if I run it again, I get it in a different point. If I run it again, I get it in a different place. A couple times it went off the screen there. We might want to change our axes. Maybe we'll make this go from -10 to 10. And we'll make the y-axis go from -10 to 10. And now we'll be sure to make sure it's on there because we're not going to get any numbers much bigger than that, right? All right, now what if I want to see what that looks like kind of in general? Here's what I can do. I can do a loop, and that's our third and last thing for this episode. We are going to say that there is a chunk of code that we want to execute a bunch of times, not just once, maybe 10 times, maybe 100 times if we want 100 points. And the way we're going to do that is we're going to say for I in 1:n, where n is the number of times I want it to go through the loop. And then again, we're going to have a pair of curly braces here, and we're going to have our statements inside the loop that are going to be executed more than once. So here's how I'm going to do that. Instead of just doing this thing once, let's come down here and say for I in 1 to 10. Put our curly braces in there. And let's indent these over. It's always a good idea to have the contents of your loop indented so that you can visually see that that part is considered inside the loop as a point, as opposed to this line down here, which actually we also want to be inside the loop, right? We want to plot each point as we get it. So I am now going to plot 10 random points. And I run that thing, you'll see there's a bunch of them here. And if I run it again, I get them there, and I get them there. Notice they're all sort of on this line. Now, they're not exactly on the line. We know, in fact, we showed a couple of segments ago that it's definitely possible to get some way out here or way over here, right? But it's less likely to get those because you're going to have to get a really extreme value of the vector in the two directions to get something up there, right? And we're just taking numbers between -2 and 2. Let's up this to 100 points. And now they all are looking like that, right? Notice if I change my domino and I say, let's make the domino go -1, 2, then it's going to have a different shape because now it's going to be much more spread out because these two dominoes are pointing in very different directions now. Or if I said, how about -11, 2? Now it's going to get really spread out, and you can't even tell there really even is a line, right? So it all depends on what the dominoes there are. But it's clear that we don't always end up exactly on a line, right? And now sort of to contrast that, let's do our blue dominoes case. So I believe our dominoes were 2, 3, and 4, 6. And now, if I plot 100 points, I always get all the points exactly on this line. There is absolutely no way to get anywhere else, because the only thing at our disposal are the points that lie on that exact line, because these are linearly dependent vectors. All right? Thanks for hanging with me through episode 3. Hope you